So once I've managed to do this magic of the holodeck and I've got you there and you've got everything that you need that's in the cloud, we kind of hit another snag, right? The snag is that typically our EDA workflows are filer-based. We have a shared file workflow model where multiple compute nodes can see each other's results, right? So that they can run successive jobs, or they can enforce a bunch of parallelism like we do, corners and multiple data gathering approaches so that we can have a top-level view. But in the cloud, we have a very, very high density of compute nodes, and we only have block stores. There isn't really a shared storage or a shared file workflow available in the clouds because that's not how they've evolved or developed. So, how's everybody else doing this? Well, let's look how software did it. That's option one. They rewrote their tools and their flows, right? And they adopted what was called a microservices architecture. This was originally pioneered by Netflix, and their chief cloud architect was Adrian Cockcroft. And they came up with an architecture where you deploy software applications as modular services. So you just slice it all up, and everything's modular, and you share data only at the very end. There's very little sharing that occurs between these services till later. That's very, very impractical for EDA and HPC, high-performance compute hardware design. We have way too many interdependencies to modularize, right? It is absolutely almost impossible to say I'm going to slice these big chips into these smaller pieces because we have to deal with physical issues, physical proximity, and physical interaction at the device layers, right? So we can't slice it up. On top of that, there's a whole bunch of legacy tools that we've been using for, don't ask me how long, right, that are just essentially impossible to convert. You're not going to be able to rewrite those. At least if you are going to rewrite them, the risk of rewriting them is too big because, unlike software, we can't ship patches to our hardware. You could roll your own filer, right? Unfortunately, filers are scale-up, right? The cloud offers all of this high-density compute, which is scale-out. So now, if you try and even roll your own filer, you've got this mismatch. You're trying to apply a scale-up storage solution or a file solution with a scale-out compute. And this mismatch results in the inability for your I/O to keep up, leading your applications to become I/O-bound, even though you have all of this compute. We see it already today, right? We see that today on-prem, our filers are really struggling to keep up, and buying more filers isn't really helping us because our filers are giving us capacity, and they're not giving us the I/O that we need. You could try an external filer, but, that's going to be even worse. You could test a new file system. I believe, I'm not sure exactly, maybe Derek knows the exact number, but I believe there are 20 to 200 storage startups all trying to do something to solve this problem. The reason why is, typically, high-performance storage is a multi-billion-dollar market, and a lot of people are trying to go after it. However, if you want to build an HPC model in the cloud using all flash for semiconductor, you're going to be broke really quickly. You can certainly do it. You can write those big checks. You can get massive amounts of custom hardware and flash and do it all. But flash memory fundamentally, from a semiconductor perspective, is not scaling the way magnetic media is scaling, right? So what you end up here is burning a lot of cash. Alternatively, right, we introduce Pure Cache, scale-out I/O that delivers extreme file performance. We have about 70 person-years of development behind the tool. So what we do is that we take advantage of local NVMe, and we provide a shared storage model for that cache using peer-to-peer.